In this video we look at the sum to infinity of geometric series. If we consider the geometric sequence 5, 10 over 3, 20 over 9, 40 over 27, etc., which has got first term 5 and a common ratio of 2/3, remembering that the sum of the first n terms of a geometric sequence with first term a and common ratio r can be written either as a times r to the n minus 1 over r minus 1, or as a times 1 minus r to the n over 1 minus r, we can write down the sum of the first n terms of this sequence as 5 times by 1 minus 2/3 to the power n over 1 minus 2/3. Now 1 minus 2/3 is the same thing as a third, and 5 divided by a third gives me 15. So I can write Sn as being 15 times by 1 minus 2/3 to the power n. Now as n gets very, very large, 2/3 to the n gets smaller and smaller. It gets closer and closer to 0. So the expression for Sn is going to get closer and closer to 15. And we say that 15 is the sum to infinity of the geometric sequence 5, 10/3, 20 over 9, etc. So we can see this in terms of a small video. So what we've got here is one term of the sequence gives me a sum of 5, two terms of the sequence gives me a sum just over 8. The more terms I take, we can see the sum is getting closer and closer to 15. In general, the sum of the first n terms of the geometric progression a, ar squared, ar cubed, etc. is given by either a times r to the n minus 1 over r minus 1, or a times 1 minus r to the n over 1 minus r. If the value of r lies between minus 1 and 1, then as n tends to infinity, the value of r to the n will tend to 0, which means that the sum of the n terms will get closer and closer to a over 1 minus r, which means that we can say if r lies between minus 1 and 1, then the geometric series a plus ar squared plus ar cubed, etc. possesses a sum to infinity, which we will denote by s infinity, given by s infinity is a over 1 minus r. So let's have a look at a couple of examples making use of the sum to infinity. Harrison and Luca play a simple game which involves taking turns to toss a bias coin which has probability 0.6 of landing on heads. The winner is the first boy to toss a head. We're going to let Hn denote the probability that Harrison wins the game on his nth toss. And the first thing we've got to do is explain why Hn is equal to 0.6 times by 0.16 to the power n minus 1. Well, Hn is the probability that Harrison wins the game on his nth toss. So that means that the first n minus 1 tosses by Harrison and the first n minus 1 tosses by Luca must all have ended up as being tails, and that then Harrison's nth toss must be a head. So we've got Hn is the probability that we get 2n minus 2 tails followed by a head from this coin. The probability of 2n minus 2 tails is going to be 0.4 to the power 2n minus 2, and this must be multiplied by 0.6, which is the probability of Harrison obtaining his head. 0.4 to the 2n minus 2. Well, we've got a common factor of 2 in the power, so we can say that 0.4 to the 2n minus 2 is the same thing as 0.4 squared all to the power n minus 1. So we can rewrite hn as being 0.4 squared to the power n minus 1 times by 0.6. In other words, hn is 0.16 to the power n minus 1 multiplied by 0.6, which of course is the same as 0.6 times by 0.16 to the power n minus 1. Now we should really notice at this stage that this is exactly the format of a geometric sequence whose first term is 0.6 and whose common ratio is 0.16. The probability that Harrison wins the game is going to be the probability he wins on the first go, or the second go, or the third go, or the fourth go, etc., which is h1 plus h2 plus h3, etc. So we've got the probability Harrison wins the game is 0.6 plus 0.6 times 0.16 plus 0.6 times 0.16 squared, and so on. So this is the sum to infinity of a geometric sequence whose first term is 0.6 and whose common ratio is 0.16. So we can say that the sum to infinity is a over 1 minus r, so that's going to be 0.6 over 1 minus 0.16, which gives me 0.6 over 0.84, or equivalently 5/7. So Harrison has a 5/7 chance of winning this game, and Luca has a 2/7 chance of winning the game. Moving on to our second example, we've got to find the first 4 terms of the geometric sequences which have a sum to infinity of 64 and a second term of 12. We know that the sum to infinity of a geometric sequence is a over 1 minus r, so I know that a over 1 minus r has to equal 64. In other words, that a is equal to 64 times 1 minus r. I'm also told that the second term of the geometric sequence is 12. So that tells me that a times r must equal 12. Substituting for a gives me 64 times 1 minus r, that's a, multiplied by r must equal 12. Dividing through by 4 gives me 16 times 1 minus r times r must equal 3. Multiplying out and getting all the terms on one side, we've got 16r squared minus 16r plus 3 must equal 0, which factorises as 0 equals 4r minus 3 times 4r minus 1. In other words, we've got r must equal 3/4 or 1/4. If r equals 3/4, then we've got a must be 64 times by 1 minus r, which gives me 16, in which case the first 4 terms of the geometric progression with a equals 16 and r equals 3/4 are 16, 12, 9 and 6.75. On the other hand, if r equals 1/4, then a is 64 times 1 minus r, which gives me 64 times 3/4, which is 48. So the first 4 terms of the geometric sequence with a equals 48 and r equals 1/4 are going to be 48, 12, 3 and 0.75. And that concludes our look at the sum to infinity of a geometric series.